Ever get that feeling like you're trying to put together a puzzle of, well, reality itself, but the pieces are just barely out of reach?
That's a great way to put it.
Well, today you've brought some truly fascinating pieces to the table, and we're ready to dive deep.
Deep into how everything, the strangeness of quantum particles, the mind-boggling scale of the cosmos, even just the way you experience the world, could all be connected, like way more than we usually imagine.
It's about seeing that bigger picture, right?
Yeah.
You've curated an amazing set of sources that really get into the nitty-gritty of what reality is, from how complex systems integrate and adapt to what's happening at the cutting edge of quantum computing,
Yeah.
even the fabric of space-time itself.
Oh, and we can't forget about your own senses. How you perceive the world, that's a big part of this puzzle, too. It's all connected.
Absolutely. Glancing through, we've got everything here. Philosophical deep dives into the very essence of reality, hardcore technical descriptions of quantum systems. It's a pretty diverse mix. And our mission today is to take all these seemingly separate ideas and weave them into a new perspective, something that's both unified and hopefully really eye-opening.
Yeah, that's the goal.
So shall we jump in?
Let's do it.
One of the things that struck me right away is this idea of a completely interconnected universe. This integrated view, as one of the sources calls it. Like, reality isn't just a bunch of isolated things floating around.
It's more like a dynamic web, right?
Yeah,
Everything's constantly influencing everything else.
exactly. Every scale imaginable, from the tiniest quantum vibrations to the largest cosmic structures, like a giant feedback loop, but with some kind of underlying purpose driving it all.
There's this amazing dance happening between those delicate quantum states, what we call quantum coherence, and the complex world that we see all around us.
Give me an example of what you mean.
Well, think about things like supersolids matter that acts like both a solid and a fluid at the same time, or how life itself organizes into these incredibly intricate, interconnected systems. It's this interplay between the quantum realm and the macroscopic world that makes it all tick.
This is where it gets really mind-blowing for me, because this interconnectedness might even extend to how we think and experience consciousness itself. It's not just the brain as a biological computer, but maybe something more fundamental, something emerging from this dynamic, almost fractal-like organization happening at multiple levels of reality?
And that challenges the way we've traditionally thought about things. The boundaries we've drawn between quantum, biological, and cosmological might be more artificial than we realize.
It's like those distinctions are starting to blur.
Right. What if, instead of separate categories, we're looking at a seamless system of energy flows and interdependent relationships?
Yeah.
And all of it's in constant flux, constantly adapting.
So it's a pretty major shift in perspective.
It is. We're moving away from the idea of static matter just hanging out in empty space and towards this concept of a self-organizing, adaptive whole.
It almost sounds like reality is more alive than we've given it credit for.
That's a great way to put it. And this is where the source lays out this unified framework. Biological systems, quantum systems, cosmic systems, they're not separate players. They're all interwoven into this coherent matrix. And it's this matrix that seems to give rise to complexity, to the emergence of new phenomena, maybe even to consciousness itself.
Okay, wow. So from this grand interconnected view of the universe, let's shift gears a bit. One of the other sources dives into the world of quantum computing, and there's this concept that really caught my eye. A decoherence-proof quantum copper system. And get this, it operates at room temperature.
Now that's a game changer.
Right. Anyone who's even a little familiar with quantum computing knows how finicky those quantum states are. They're so fragile that they require incredibly cold temperatures, close to absolute zero, just to function.
Yeah, and even then, you're constantly battling decoherence, the tendency of those states to collapse due to any little disturbance in the environment. And then you've got all these complex error correction mechanisms on top of that.
But this quantum copper system is inherently resistant to decoherence. It just functions at room temperature, potentially bypassing a ton of those engineering hurdles.
It's like having a quantum computer without needing a giant supercooled refrigerator. That's a pretty big deal.
So let's get into what this actually means for what these computers can do. The source mentions deterministic quantum operations. Can you unpack that a bit?
Sure. In traditional quantum systems, you've got this inherent probabilistic nature. It's like rolling a quantum dice, so to speak, which can make them tricky to control. But because the quantum copper system is much more stable, the operations become far more predictable and reliable.
So you get more consistent, reproducible results.
Exactly. And that also has huge implications for the design of the system itself. You don't need as much complex machinery dedicated to just keeping the quantum states from collapsing.
And then there's this idea of scalability, which always seems to be a major bottleneck in any new technology. The source highlights how this system could be scaled up much more easily.
That's a huge advantage. The modular nature of the quantum copper system means you can essentially plug in more processing units as needed. No complete overhaul, which makes it much more practical to build truly powerful quantum computers.
This is where it gets interesting, the connection to that interconnectedness we were talking about earlier. The source then brings in these thermopower measurements in fractional quantum Hall states. Now, for someone who's not a quantum physicist, how does measuring heat relate to controlling these incredibly tiny quantum systems?
It's a fascinating link, actually. Thermopower, also known as the Seebeck coefficient, essentially tells us how much voltage a material generates when there's a temperature difference across it. What's really interesting is that in these fractional quantum Hall states, thermopower is directly related to entropy,
And just to remind our listeners, entropy is a measure of.
disorder or randomness within a system. The more entropy, the more chaotic things are.
Right. Okay, so back to these measurements.
So we can actually use thermopower to measure the entropy contribution from the spin of these weird particles called quasiparticles, which behave like fractions of electrons. It's like using heat as a window into the quantum world.
So more heat, more disorder,
Yeah.
and that affects these delicate computations.
Exactly. And the source proposes using these thermopower measurements as a real-time feedback mechanism. You can imagine it like having a built-in thermometer for your quantum system.
And based on the temperature, you can adjust things to keep the system running smoothly.
That's the idea. For example, low entropy states are ideal for stable, simple computations, while high entropy states might be better for exploring more complex quantum phenomena. And they propose integrating this entropy metric directly into the system's control architecture.
So it's constantly monitoring and adjusting based on the thermodynamic state of the system. And that brings us to the quantum path optimizer, the AI-driven brain behind all of this. It's using reinforcement learning, right, to basically find the best way to run these computations.
Precisely. It's like a super smart navigation system, but instead of finding the fastest route on a map, it's figuring out the most efficient sequence of quantum operations to achieve a desired result. And here's the cool part. It doesn't just look at traditional metrics like speed or accuracy.
It also factors in this entropy data.
Right, it's doing entropy-aware optimization. This means the AI can select computational paths that are not only fast and accurate, but also thermodynamically stable.
Less likely to cause errors or decoherence.
Exactly. The source even talks about these hybrid optimization approaches, combining different computational techniques while always keeping an eye on those entropy constraints.
It's all about that balance between power and stability.
Absolutely. And this constant loop of thermodynamic monitoring and AI optimization, it allows the system to learn and adapt on the fly, ensuring peak performance.
It almost sounds like it's self-aware, in a way.
In a sense, yes. It's constantly adjusting to stay in that sweet spot, and this whole approach opens up a world of possibilities for real-world applications.
Like edge quantum computing, for instance.
Yeah, the fact that it works at room temperature makes it much more practical to put quantum computing power in all sorts of places, like mobile devices or embedded systems. It doesn't have to be confined to a specialized lab anymore.
What about continuous quantum processing? Running those complex computations for long periods of time.
Well, the stability of the quantum copper system makes that far more achievable. And the entropy-aware optimization is crucial for maintaining accuracy over those long hauls. It prevents the system from drifting into those unwanted states.
And scalable quantum networks. That seems huge, the idea of interconnected quantum computers across distances.
That's the ultimate goal. But maintaining that quantum entanglement over long distances, it's incredibly difficult. Room temperature, stable qubits with this kind of thermodynamic self-monitoring could be the key to making those networks a reality.
The source even includes a nice visual overview of the whole setup. The control systems, the quantum copper system, the optimization engine. You can really see how it all comes together.
It's a cohesive, sophisticated platform. And the takeaway here is the synergy between fundamental physics, those thermodynamic principles, and these really advanced computational techniques like AI.
It's like we're finally getting to a point where we can harness the power of the quantum world in a practical way.
That's the exciting part. This could lead to a whole new era of technology, impacting just about every industry you can imagine.
Okay, shifting gears a bit, but still staying in the realm of interconnectedness and the fundamental nature of reality. Your next source takes us into some mind-bending territory. We're talking an energy-centric theory of everything, higher dimensions, even the possibility of time travel without those pesky paradoxes.
This is where we really start pushing the boundaries of our current scientific understanding.
Definitely. The source starts by laying out this idea that energy, in all its forms, is the most fundamental building block of the universe. And it points out those current estimates. 68% dark energy, 27% dark matter, and only a tiny 5% of the universe being the regular matter that we can see and interact with.
It really highlights how much we still don't know about the universe. All that dark stuff is a pretty big mystery.
A huge mystery.
Right. And this theoretical framework suggests that maybe we can think of the universe as a system where potential energy residing in dark energy and dark matter constantly interacts with kinetic energy, the energy of motion that we see as regular matter. And this interplay is happening within a framework that goes beyond our familiar four dimensions of space-time.
This is where the higher dimensions come in, right? The source mentions a mathematical transformation that turns our 4D spacetime into a 5D Riemannian manifold.
Yeah, imagine our usual 4D space-time as a flat sheet. Now picture bending and curving that sheet, not just in 3 dimensions, but in 5. That's what a Riemannian manifold is like. It's a more complex geometric structure that allows for the inclusion of extra fields and coordinates that could describe aspects of reality that our current 4D model just can't capture.
And this fifth dimension, what could it represent?
Well, there are a couple of intriguing possibilities. It could be related to thermodynamic properties, things like entropy and temperature gradients, suggesting a link between the large-scale laws of thermodynamics and the very structure of space-time. Or it could represent a hidden spatial dimension, one that plays a role in how dark energy and dark matter behave.
So either way, it's adding another layer to reality as we know it.
It is. And one of the most exciting prospects here is that this 5D framework could finally bridge the gap between quantum mechanics, which governs the very small, and general relativity, Einstein's theory of gravity that describes the large-scale structure of the universe.
Those two are like the pillars of modern physics, but they haven't quite fit together seamlessly.
Exactly. They've been notoriously difficult to reconcile. But by embedding those quantum fields and wave functions into this richer 5D geometric structure, we might have a mathematical language that can describe how they both emerge from a single underlying reality.
Okay, so we've got this 5D manifold, this potential bridge between quantum mechanics and relativity. And then the source throws in this thermoacoustic wave equation.
This is where it gets really cool.
I usually associate thermoacoustic with, sound and heat interacting. How does that apply to the fabric of space-time itself?
Imagine these thermoacoustic waves as ripples in space-time, disturbances caused by fluctuations in energy density. And this includes not just the energy of regular matter, but also the energy of dark matter and dark energy. And these waves can propagate through this 5D manifold, potentially creating a way for the visible and dark sectors of the universe to interact.
So it's like the universe is constantly vibrating with these waves, driven by the ebb and flow of energy, both light and dark.
And the source points out this fascinating parallel between these thermoacoustic waves and Schrödinger's equation, the equation that describes the evolution of quantum wave functions. It's a possible link between the very large and the very small, suggesting that they might be governed by similar mathematical principles.
Mind blown. Again.
Right. And then there's this concept of a universal Hilbert space. In quantum mechanics, Hilbert space is like this abstract mathematical arena where all possible states of a quantum system can exist.
All the possibilities, all laid out.
Exactly. Now imagine a Hilbert space that encompasses all possible states of the entire universe.
Whoa.
Yeah. And the source proposes that 95% of this universal Hilbert space is occupied by states corresponding to dark energy and dark matter, while only a tiny 5% is dedicated to the states we observe as regular matter.
That makes sense, given those cosmological estimates we talked about earlier.
Right. And within this universal Hilbert space, Schrödinger's equation would govern how the universe's overall state evolves, describing how those transitions between potential and kinetic energy states happen over time.
So we've got quantum mechanics describing those probabilities at the smallest scales, these thermoacoustic waves describing the dynamics at the largest scales. And this 5D manifold could be where those two seemingly different descriptions converge.
It's a compelling possibility. Imagine those tiny quantum fluctuations at the Planck scale rippling outwards, giving rise to these macroscopic perturbations in the very fabric of spacetime.
Okay, I need a moment to process that. All right, I'm ready for the next mind-bending concept, time travel. The source suggests that this 5D framework could actually allow for closed time-like curves, essentially time loops, but without those paradoxes that always seem to crop up.
The classic grandfather paradox, going back in time to prevent your own birth, yeah, those get messy fast. But within this 5D framework, the rules of cause and effect might operate in a more complex, multidimensional way.
So higher dimensional causality.
Exactly. Think of it like this. Interactions happening within that higher dimension could set up constraints that prevent those paradoxical scenarios from even emerging in the 4D spacetime that we experience.
And the probabilistic nature of quantum mechanics, described by Schrödinger's equation, could also play a role in maintaining consistency.
Absolutely. Those closed, time-like curves could represent a superposition of all possible timelines rather than just a single fixed loop. It's that quantum fuzziness that could smooth out those paradoxes and allow for self-consistent histories.
And even those thermoacoustic waves we were talking about could contribute to stabilizing those time loops.
The source suggests that those waves might act to dampen any disturbances in space-time geometry that could lead to paradoxical outcomes. It's like they're ensuring those time loops remain consistent with the fundamental laws of physics.
Okay, so to sum up this incredibly dense source, we're looking at a unified picture where the universe is a dynamic 5D Riemannian manifold. Quantum mechanics governs those fundamental processes within a universal Hilbert space. Thermoacoustic waves are describing the large-scale dynamics, and even time travel could be possible without destroying reality as we know it. Did I get all that right?
You got it. It's a pretty bold and ambitious framework, but it gives us this fascinating glimpse into how all these seemingly disparate pieces of physics might actually fit together. Classical physics, quantum mechanics, thermodynamics, and relativity, all woven into a more coherent understanding of the universe.
Amazing. Okay, after that wild ride into the depths of theoretical physics, let's bring things back down to earth, literally, and talk about your own sensory experience. The next source dives into this fascinating idea that our senses might actually have a quantum basis.
It's all about questioning whether those seemingly ordinary ways we perceive the world, sight, sound, touch, taste, smell, could be rooted in quantum mechanisms that we're just beginning to understand.
It's a whole new way to think about our senses. The source starts by laying out the basics, the types of stimuli each sense detects, the sensory organs involved, and those key parameters like wavelength for vision or frequency for sound.
And the absolute thresholds, those minimum levels of stimulus needed for detection, and the just noticeable differences, how much change is needed before we perceive a difference.
Right, the fundamentals.
Yeah.
But then it takes this quantum leap, suggesting that we could potentially map these sensory parameters onto a theoretical model called a 5-photon noon state. Now, for our listeners who aren't familiar with quantum physics jargon, can you explain what a noon state is?
Sure. It's a very specific type of quantum state involving photons, those particles of light. Imagine 5 photons all linked together in this weird quantum way, where they're all simultaneously in multiple states. That's a noon state.
A state of being in multiple places at once.
That's the essence of quantum superposition. And what makes noon states so interesting is that they're incredibly sensitive to changes in phase, the timing of a wave, even more sensitive than classical light sources. So they hold this potential for ultra-high precision measurements.
And they're suggesting that this ultrasensitivity could be how our senses work.
It's a radical idea, but stick with me. Let's take vision, for example. The source proposes that we could map the wavelength of light, which our brains interpret as color, to a phase shift in a 5-photon noon state.
So different wavelengths, different colors, different phase shifts in the noon state.
Exactly. And because those noon states are so incredibly sensitive to even tiny changes in phase, it means our visual system could theoretically detect those minute variations in wavelength with much higher precision than we currently think is possible.
And what about the intensity of light, how bright or dim something appears?
That could be mapped to the number of photons in the noon state. More photons, brighter light.
And they extend this same logic to hearing, touch, even taste and smell.
Yep. For hearing, frequency, which we perceive as pitch, would be mapped to a phase shift, and amplitude, or loudness, to the number of photons. For touch, they propose mapping vibrations to phase shift and temperature to the distribution of photons in that noon state. It's a pretty radical departure from how we normally think about feeling a texture or sensing heat.
It's definitely mind-bending. But I love how this source is pushing the boundaries. What about taste and smell? How do they fit into this quantum picture?
For taste, they suggest mapping the concentration of chemicals, which determine how strong a flavor is, to a phase shift. And get this, they even propose that different flavor profiles themselves, like sweet or sour or salty, could be encoded as quantum superpositions of different photon modes.
Whoa, quantum tasting. That's amazing.
Right. And for smell, similar to taste, the concentration of those volatile chemicals, the things we actually smell, could map to a phase shift.
Mhm.
Different types of molecules would correspond to different configurations of those photon modes.
It's like our senses might be tapping into the strangeness of quantum mechanics, using superposition and entanglement to achieve this incredible sensitivity and ability to make sense of the world around us.
And the source highlights how this could have huge implications for technology, too.
Quantum sensing.
Exactly. Imagine building ultrasensitive cameras based on these quantum principles of vision, or developing acoustic sensors that can pick up sounds we can't even hear with our ears.
That's some next level tech right there.
And it could revolutionize fields like neuroscience and AI, too. Imagine building AI systems that integrate multisensory information in a truly quantum way, like our brains do, but even more powerfully.
And it brings up some profound philosophical questions, too. If our very perception of reality could be based on quantum mechanics, what does that really say about how we experience and interact with the world? Is there a deeper quantum layer to consciousness itself?
Those are the big questions, and they're wide open. This source really challenges us to rethink how we understand both our inner and outer worlds.
I'm still processing all of that.
Okay,
Ready for the grand finale. The last source you brought builds on all of this, proposing a framework that maps not just space-time but human cognition itself onto that 5D Riemannian manifold we were talking about earlier.
this is a big one, a truly ambitious attempt to unify the cosmos and the mind within a single mathematical framework. And it starts with those foundational dimensions: zero-dimensional space as just a single point, and one-dimensional time as a linear progression of moments.
Okay, the basic building blocks of space-time.
Right. Then the model moves to two-dimensional stimuli input on the Minkowski metric plane.
Just a quick reminder for our listeners, the Minkowski metric is.
It's the mathematical structure we use in Einstein's special relativity to describe the geometry of spacetime. It basically combines space and time into a single four-dimensional continuum. And in this model, they're picturing this two-dimensional plane as the surface where all that raw sensory data gets encoded.
So all the light hitting your retina, the sound waves hitting your eardrums, those are all mapped onto this 2D plane.
Exactly. That's the initial input. Then, the model proposes a transition to three-dimensional cognitive projection. This is where our brains take that flat 2D data and turn it into the 3D world that we perceive.
Our brains are constructing a model of reality from that sensory input.
Right. It's like our brains are the ultimate 3D printers.
Love that analogy.
Mm.
Okay, so 3D perception, that's how we navigate and interact with our world. And then the model jumps to a fourth dimension, consciousness.
And this dimension extends beyond that immediate 3D perceptual experience. It encompasses our thoughts, our memories, our sense of self that persists through time. It's a more non-local, non-linear dimension where the rules of 3D space and time might not strictly apply.
So memory isn't just a linear recording of the past, it's something more interconnected and existing outside those normal constraints.
Right. And the source even hints at a connection with quantum cognition, suggesting our thoughts and memories might operate in ways that share similarities with how quantum wave functions behave.
Very cool. All right, and finally we reach the fifth dimension, the realm of bulk information.
This is where things get really interesting. The source suggests that this fifth dimension is where all the information from those lower dimensions, from 2D stimuli all the way up to our 4D conscious experience, gets encoded. And it's encoded back on that original 2D Minkowski plane, but then projected into that 5D Riemannian manifold that we talked about earlier.
So it's like that 2D plane is a holographic surface containing information about a much larger, higher dimensional reality.
Exactly. And this could be related to those holographic principles we see in cosmology and string theory. The idea that information about a higher dimensional volume can be encoded on its lower dimensional boundary. It's mind-blowing to think that our 2D sensory input could be holding clues to this vast, multidimensional reality.
Definitely mind-blowing. And, as complex as this framework is, it actually feels like a natural progression from all those previous sources we talked about. It's like they're all converging on this idea that our perception, those five senses that we rely on, might only be showing us a tiny sliver of what's actually out there.
and that there's a much deeper, more interconnected reality waiting to be discovered.
And that those tools from quantum mechanics and those higher dimensional mathematical frameworks, they could be the key to unlocking that deeper understanding.
That's the really exciting part. It's like we're finally starting to see a path forward.
Okay, I think our brains might be officially fried after all of that.
I think mine is too.
But in a good way, I hope. From that fundamental interconnectedness that seems to permeate reality at its deepest level, to the mind-bending possibilities within quantum computing, the potential links between the structure of space-time itself and the quantum nature of our own perception. It really does feel like we're just beginning to scratch the surface of a truly integrated understanding of everything.
And hopefully this deep dive has given you, the learner, some new perspectives to ponder, some fresh ways to think about these big questions.
Absolutely. We've covered a lot of ground today, but here's a final thought to leave you with. If both our most intimate sensory experiences and those fundamental forces governing the universe can be explored through this shared language of quantum mechanics and higher dimensional geometries, what does that say about the very nature of information itself? And what does it mean for us, those conscious observers, embedded within this vast and dynamic reality?
It's a question worth contemplating.
Definitely. And remember, this is just one deep dive, one snapshot in time. The quest for knowledge is an ongoing journey, and we encourage you to keep exploring, keep asking those big questions, and see what other surprising connections you might uncover along the way.
You never know what you might find.
Exactly. Until next time, happy exploring.
Keep diving deep.